When you observe those classic European portraits, or even just look at prominent figures today, there's often one feature that really stands out.
The high-bridged projecting nose.
Exactly. And we're sort of taught to see that shape purely through, I guess, the lens of art or just simple genetic difference.
That's so true. We just file it under racial traits or, beauty standards. But if you really get into the source material, a completely different story emerges.
A much more interesting one.
Way more interesting. That specific facial architecture, it isn't about fitting a fashion mold. It's actually a meticulously crafted biological defense mechanism.
It's a blueprint for survival.
A blueprint for survival written by climate and the urgent need to conquer the cold.
And that is our mission for this deep dive. We're going to unpack some really robust research from 19th century anatomical studies, modern 3D scanning, all the way down to the DNA.
And even a bit of ancient history.
Right. To really understand why this physical trait is, at its heart, a piece of biological engineering. To start, you have to stop seeing the nose as just a feature and start seeing it as the body's most critical air conditioning system.
And we have the sources to back it up. We're talking Arthur Thomson's original observations, huge population studies from Penn State, and even the specific genes like DCHS2 and RUNX2.
Okay, so let's find out definitively why the prominent European nose is, well, nature's perfect heater.
Let's do it.
So let's unpack this. We have to start where the whole scientific journey began, right? With a man named Arthur Thomson in the 19th century.
Right. He gave us what's known as Thomson's rule, the foundational principle.
So what exactly was his observation? How did he start categorizing human noses in the first place?
Well, Arthur Thomson was a British anatomist, and he was doing what a lot of anatomists did back then. He was measuring human skulls from all over the world.
And he just noticed a pattern.
A very clear, very repeatable statistical pattern. Thomson's rule basically formalized this relationship he saw between geography and nose shape.
Okay, so what was the rule?
Populations whose ancestry traces back to cold, dry climates, they tend to have narrower and longer noses, what we would call more prominent or high-bridged.
And what about people from warmer regions?
He saw the exact opposite. Populations near the equator, where it's hot and humid, they consistently showed wider, shorter, and flatter noses.
That's too consistent to be just random chance.
Exactly. It strongly suggested a long history of environmental selection was at work.
The huge question then is why? I mean, it almost seems counterintuitive, right? That a smaller, narrower opening would be better for survival.
It does, until you consider the fragility of our internal organs, specifically our lungs.
Tell us about that. What are the biological demands of the human lung?
The entire respiratory system, especially the lungs, is remarkably sensitive. They need the air they receive to be in a very narrow band of temperature and humidity.
So close to body temperature and fully moist.
Ideally, yes. If you breathe in air that is drastically cold and, maybe more importantly, critically dry, it's like a slow-motion biological attack.
So if you're living through a long European winter, that freezing dry air is constantly trying to, damage the inside of your airway.
Precisely. Inhaling cold, dry air directly can cause inflammation, it dries out the protective mucus, and it can actually chill the cilia.
Those are the tiny little hairs that clean out your lungs.
The very same. And all that stress makes your respiratory tract highly vulnerable to infection, to damage. For early humans in Europe, surviving the winter often came down to surviving lung infections.
So the prominent nose evolved as a highly optimized countermeasure. How does that extended narrow geometry actually do the job of warming and humidifying the air?
It's a brilliant piece of biological engineering, really. It works with three synergistic actions. First, the high bridge increases the total surface area inside the nasal cavity.
Like adding more fins to a radiator.
That's a perfect analogy.
Yeah.
Second, that prominence dramatically increases the distance the air has to travel before it even gets to the back of your throat.
And the third action, this seems like the most critical one, is about the airflow itself.
It is. Because the channels are so narrow, the air can't just rush straight through.
It's forced to slow down.
It's forced into intense turbulence. It swirls and mixes like crazy. This slowing and swirling maximizes the contact time with the thick, blood-rich mucous membranes.
And the blood is the heat source.
The blood is the heat source, and the mucous membranes provide the moisture.
So if we were to design a machine today to condition air for the lungs in an Arctic climate, we'd build something that maximizes surface area and contact time and slows the air down.
And that is exactly what the narrow, prominent nose does. It is a highly, highly efficient heat exchanger.
That's the key takeaway, then. The structure preconditions the air, makes it safe for the lungs, and that gave our ancestors a huge survival advantage.
An immense advantage, selected for over countless generations.
So, if Thomson gave us the theory back in the 19th century, the 21st century is what finally gave us the hard data.
Right.
Let's talk about the research that validated this on a global scale, the big study from Pennsylvania State University.
This was a game changer. The team used modern tech, specifically 3D scanning, to measure the exact geometry of the face with incredible precision.
And they looked at a lot of people.
Over 5,000 individuals. And crucially, they included people with European, West African, and East Asian ancestries. And then they correlated those facial measurements directly with the climate data from their ancestral homes.
So this must have provided a statistical link that was just, well, undeniable. It moved the argument beyond just observation.
It absolutely did. The key finding was a direct, statistically powerful correlation that confirmed Thomson's idea from a century ago.
So what specifically did they find?
They found that no structure, so how wide the base is, the breadth of the nostrils, the height of the bridge, it's all directly tied to that ancestral region's average temperature and relative humidity.
The environment literally sculpted the face over thousands of generations.
It did. They even identified what you could call a latitude index.
A latitude index.
Yeah. As they tracked human populations away from the equator and toward the poles, as latitude increases, the statistical index for nasal prominence increased significantly. It perfectly mirrored the drop in temperature and humidity.
Wow. The body evolved the exact tool needed for that specific spot on the map.
It's an incredible illustration of natural selection.
It really is. So if Europe needed this high-efficiency heater, what did the human body need in regions around the equator?
Well, the survival math flips completely. In hot, humid places like parts of Southeast Asia or Africa, the danger isn't freezing your lungs.
It's overheating your entire body. Heat stroke.
Exactly, especially during hard work like hunting. So there, the priority is efficient heat dissipation, cooling down.
And how does a wider, flatter nose structure help with cooling?
It's built for high-volume, low-resistance airflow. A flatter, wider nose gives you a wider nasal passage and a much shorter travel path.
So air can move in and out really fast.
At maximum velocity. When you exhale rapidly through a wide nose, you're dumping a maximum volume of heat and moisture very, very quickly.
So if a narrow European nose slows air down to heat it up, a wider tropical nose speeds it up to dump excess heat.
It's optimized for ventilation. You've got it.
And having a long, narrow nose in the tropics would actually be a disadvantage.
A major one. It would restrict airflow, slow down heat exchange, and potentially push you closer to heat stroke. It's the wrong tool for the job.
So the lesson here isn't that one shape is better, but that evolution optimized two different forms for two radically different challenges.
That's the ultimate lesson. Survival of the most appropriate.
It's incredible to think the difference between surviving an ice age and surviving a tropical heat wave comes down to, well, engineering on your face. Okay, let's dig even deeper, down to the absolute smallest building blocks. What are the genetic sculptors behind these huge architectural differences?
So to answer that, geneticists use a really powerful tool called a genome-wide association study, or GWAS.
GWAS, what is that in simple terms?
It's essentially a way for scientists to scan the entire human genome to find tiny variations or little switches in the DNA that are linked to a specific physical trait.
And through that, they found the genes for nose shape.
They did. They identified 4 specific genes that act as the master architects here.
Just 4 genes for a major ancestral trait. That's incredible precision.
It's remarkably precise. So the first 2 are DCHS2 and RUNX2.
Okay.
These genes are heavily involved in controlling the growth and shape of the cartilage and the bone structure underneath. In European populations, the versions of these genes that got selected for encourage that prominent projecting bridge, the sharpness of the profile.
So that pair explains the height, the projection. What about the other 2, GLI3 and PAX1?
Good question. Those seem to control the width, which is just as critical for airflow.
Right, the ventilation aspect.
Exactly. GLI3 and PX1 primarily regulate the width of the nostrils and the base of the nose. So in populations adapted for rapid cooling, these genes promote a wider structure. But in Europeans, evolution selected for variations that cause a narrowing of the nasal passages.
And that narrowing is what creates the turbulence we talked about, the key to the heat exchange.
That's the piece of the puzzle. The final shape is the result of these 4 genes working together, perfectly fine-tuned by the local climate over millennia.
This is where the story takes a really surprising historical turn, isn't it? We know modern Homo sapiens came from Africa, but this highly specialized cold weather feature, it seems to have been perfected much earlier.
By a different but related lineage,
You're
yes.
talking about Neanderthals.
I am. This is one of the most compelling recent discoveries. When our modern ancestors migrated out of Africa into Europe around 40 to 50,000 years ago, they met and interbred with Neanderthals.
And the Neanderthals were already the masters of that environment. They were perfectly adapted to the Ice Age conditions.
They absolutely were. Paleontological evidence shows they had these incredibly robust bodies, and critically for our story, they were known for having very large and highly prominent noses.
So they had their own super efficient cold conditioning system.
A highly refined one, honed over hundreds of thousands of years in extreme glacial climates.
So when our ancestors arrived, they didn't have to wait thousands of generations for their own adaptations to develop. They sort of outsourced the perfected genetic design.
That's a great way to put it. The scientific term is adaptive introgression.
Adaptive introgression.
A major study from University College London, UCL, confirmed it. They found that certain genes governing high nasal bridges in modern Europeans were directly inherited from Neanderthals during that period of interbreeding.
That genetic handoff must have been an absolute game changer. It would have accelerated our ability to thrive in those freezing environments.
It was an immediate evolutionary boost. It's hard to imagine our ancestors surviving those first brutal European winters without borrowing that pre-existing battle-tested technology.
So the prominent features on the European face today are, in a way, a direct genetic artifact, a legacy from our Ice Age cousins.
The ultimate design for optimal cold management, passed down through the generations.
We've clearly established that the environment natural selection was the primary sculptor here. But once a physical trait starts to signal good health and resilience, another evolutionary force kicks in.
Sexual selection.
Right. How did a useful nose become a socially and sexually desirable nose?
Well, the evolutionary logic is pretty simple and efficient.
Sure.
In societies that were struggling through harsh winters, if having a prominent nose meant you could breathe better, you got fewer respiratory illnesses, you were just generally healthier.
And that physical trait becomes a powerful unconscious signal.
A signal of high genetic status, of fitness.
So in effect, you're choosing a partner who has the best internal heater already installed.
Exactly. The prominent structure signaled strength and survival in a really challenging environment. Over time, in ancient European societies, this form was unconsciously linked to desirability, elegance, and vitality.
And mating preferences would just reinforce those genes generation after generation.
Cementing it as a core ancestral trait, selected for both by necessity and eventually by perceived beauty.
This has been a true deep dive. The core message here, it seems, is that the prominent European nose isn't inherently superior, but it is perfectly appropriate for the history of its environment.
It represents a 10,000-year struggle against snow and dry, freezing air.
And understanding that context is so important today, especially when you look at global beauty standards.
It is. We see in many parts of the world, including some Asian cultures, where a prominent nose is sometimes seen as the gold standard of beauty. It even leads people to seek cosmetic surgery to get that specific look.
But the sources remind us that this completely ignores the context. I mean, if your ancestors came from a hot, humid place, building a cold weather structure on your face might have actually been detrimental to survival centuries ago.
Because it slows down that critical cooling process. Exactly. The nose is a reminder that beauty is truly functional. Each shape is a perfect, optimized solution to a specific environmental problem.
The prominent nose of European ancestry is a monument to the victory over cold.
And the wider structure of tropical populations is a monument to the victory over intense heat.
So what does this all mean for us today, then?
It means we should really look past surface aesthetics and just recognize the incredible history written on the human face.
It's a whole new way of looking at people.
It really is. The next time you see a famous portrait or a statue or a model with that defining hybrid structure, ask yourself, are you just seeing beauty? Or are you looking at a biological monument?
The direct legacy of Neanderthal adaptation and genetic engineering, designed perfectly to conquer the Ice Age. It certainly makes you wonder what environmental factors shaped your own ancestral features. A fascinating thought to end on.